it again. Okay. So what is this first column? This first column, what this first column is telling you? This first column is nothing but the derivative of this vector del y by del x with respect to x1. Correct?
Yes,
What is okay? This what is the second second column? Second column again. The second column is nothing but the derivative of del y by del x vector with respect to x2. We are just using the we are just using the previous notations. Okay, whatever we have learned previously, we are again applying the same thing here in terms of stacking. Okay, and what this is and if I have to write this in more compact form, what this is effectively, this is nothing but derivative of del y by del x with respect to x prime, because it is stacking in a row form. and and how we effectively do denote a Hessian matrix. A Hessian matrix is nothing but del square y del square y divided by del x prime. Okay. So if effectively what we are doing, firstly we are finding the partial derivatives with respect to each. So firstly we are finding this partial derivative del y by del x, and it will be a column vector. Okay, and then we are differentiating with it with respect to x prime, because we have already done it with x. So the next time it has to be with respect to x prime. Okay, so since it is a column vector and we are differentiating it with respect to x prime, so all those second order partial derivatives will be stacked in a row form, and finally it will be stacked like this. That's it. So here I just wanted to show you how are we stacking in a matrix form. How we stack all these things. Okay, because we all know how to do the differentiation, right? The only thing in the matrices is how to stack all these derivatives, how to stack all these elements of the derivatives. Okay, so let's do a very small example of this differentiation. So this is a maximization problem. Suppose we want to maximize a function r, which is a prime x minus x prime ax. Okay, so if we want to maximize something, what we have to do? We have to find the first order condition with respect to the parameter, with respect to the variable for which we want to maximize the function. So since we want to maximize this function with respect to x, so then effectively what will be the first order condition? It will be del r by divided by del x, and x is a vector. Remember that x is a vector. So what it effectively means that we have to differentiate this element and this element separately with respect to x. And this we have seen earlier. The derivative of a prime x will be a, okay, and derivative of x prime ax will be 2ax. So del r by del x is nothing but a minus 2ax is equal to 0. This a is a vector, this x is a vector, both has same dimensions, and this a is a, and let's assume that this a is a non-singular matrix. Okay, this a is a non-singular matrix, because if it is non-singular, yes.
Ma'am, are we also assuming it is symmetric in nature?
No, we are not assuming that.
Ma'am, I think
Oh,
we are.
no, we are assuming, sorry, we are assuming that it is a symmetric non-singular matrix. So
Okay,
we
ma'am.
are assuming because that is why it is two-way.
2x.
Yes. Otherwise, it will be a plus a prime. Okay. So I'll add this line also. So A is a symmetric non-singular matrix. Okay. So this third line is not important. This is just for the sake of completeness. What effectively I want to show here is that suppose if you have some expression, then how to find its first derivative, first order derivative, and the second order derivative. Okay, because you should know that how we are reaching from here to here. Okay. So let's just for the sake of completeness, so we can write x is equal to 1 by 2 a inverse a. We can write this only if a is a non-singular matrix. Then only its inverse will exist. Hence I'm saying, so let's assume that a is a non-singular matrix. And of course it is a symmetric matrix. Therefore we are saying that it is, sorry, 2ax. Okay. So this first order partial derivative is fine, right? Similarly, if we want to find the second order derivative of this expression, of course, when we do maximization, so we have to check for the second order conditions also, right? So for that, what we have to do, we have to find the second order partial derivatives. Okay. So what will be the second order partial derivative of this thing? It will be del square r divided by del x prime. Okay. Please remember these notations. People often make these mistakes. They write del x prime, del x, and sometimes they don't even write x prime. They just write del x, del x. These small things are really important. And these small things are going to determine this last thing. Okay. This I have shown you earlier also. That say if you are differentiating ax with respect to x prime, then it will be a. But if we are differentiating ax with respect to x, it will be a prime. Okay. So these small things are important. If you are mixing all these things, effectively you are doing a wrong thing. Okay? So now what we are doing, we are differentiating this expression with respect to x prime. Okay. Since we are differentiating this expression with respect to x prime, so this will be 0 because it has no element of x. And here what we are doing, we are differentiating ax with respect to x prime, and we have just seen that differentiating this with respect to x prime is nothing but a. Okay. So del square r by del x prime is nothing but minus 2. Okay. So far, so good. I hope this is clear. So this was a very small example of matrix differentiation where we are going to use all those stuff which we have just studied. Uh, where you are going to use this matrix differentiation uh, effectively in this semester when you are going to do OLS in matrix form. So you know that we have to minimize the sum of the square sum. We have to minimize the sum of the squares of the errors. Okay, so there you are going to use all these things because there we are going to perform a minimization exercise. So minimization exercise will going to involve the differentiation of some expression with respect to some vector. So there you are going to use all these things. Hence this stuff is important, how to do the matrix differentiation. Okay, so that's it on the matrix differentiation. I just have to cover a very small thing now. Uh, this is about the definite matrices, definites of the matrices. So a quadratic form A can be, I mean, you guys should know that what is meant by positive definite matrix and positive semi-definite matrices. If you guys don't know, pick any standard maths textbook and read it from there. Here I'm just going to draw attention to the fact that how the characteristic roots, I mean the eigenvalues and the definiteness of a matrix are related to each other. Okay. I don't know this is going to be useful or not, but just for the sake of completeness, because we have talked about, we have little bit talked about the quadratic forms and we have talked about the eigenvalues. So just for the sake of completeness, this is important. That how the characteristic roots and the definiteness of a matrix are related to each other. Okay. So we have already seen that a quadratic form Q can be written as x prime ax. Now here A is a symmetric matrix. So we are talking about a symmetric matrix only. So if all the characteristic roots of a matrix A, of symmetric matrix A, are positive, then a matrix A is matrix. So has n eigenvalues. Then if all the n eigenvalues are positive, non-zero positive, then we say that a matrix A is a positive definite matrix. And if all the eigenvalues are negative, then we say that the matrix A is a negative definite matrix. Okay? So for example, in the first example, if I correctly remember, when we were doing the first example, but it was not a symmetric matrix, I guess. Sorry. So suppose if there is a symmetric matrix and if all the eigenvalues are positive, then it is a positive definite matrix. And if all the characteristics groups are negative, then it is a negative definite matrix. Uh, uh, and if some of the roots are zero and some are positive. We have seen an example in which there was, although it was not a symmetric matrix, if I remember it correctly, but just to draw an analogy, we have seen an example that we can have some cases where.
Sorry to interrupt you, but you're not clearly audible.
Okay. So I am saying that suppose if a symmetric matrix A has eigenvalues such that some of the eigenvalues are zero, but some of them are positive. Either they are zero or positive, then we say that it is a positive semi-definite matrix or a non-negative definite matrix. But if a matrix A has some eigenvalues as zero and some are negative, then we say that it is a negative semi-definite matrix or a non-positive definite matrix. That's what I'm saying. Okay. So if all the eigenvalues are either positive or negative, then it is a positive or negative definite matrix. But if some of the eigenvalues are zero or positive, then we say it is a positive semi-definite matrix. And if some of the eigenvalues are zero or negative, then we say that it is a negative semi-definite matrix. And if a matrix has both negative and positive roots, both negative and positive eigenvalues, then we cannot say, then we say that A is an indefinite matrix. That's it. That's it. How the characteristics roots and definite values are related to each other. Okay. So I hope it's clear. So, so that's all. Okay. So I, yeah. So that's it. That's all what I have to cover. If anybody has any question, then you guys can ask.
Ma'am, can you once repeat how the Jacobian matrix is stacked?
Yeah, sure, no problem. Yeah. So this is how we stack a Jacobian matrix. So you understood that what is a Jacobian matrix? Jacobian matrix is nothing but a matrix of its first order partial derivatives. Okay. Uh, of a vector valued function. Okay. So how to denote a Jacobian matrix? What is the notation? A Jacobian matrix is denoted by capital letter J, which is effectively del F over del X prime. Okay. So del F, or we can say it as del Y also, because Y is nothing but F of X. So del F over del X prime, and what it effectively means, that we are going to differentiate each element of F with respect to each element of vector X and stack it in a row form. So it means that we are differentiating vector F with respect to x1, and then we are differentiating F with respect to x2 and stacking it in a row form up to del F over del xn. So uh, this is how so this is what is meant by x prime, and since F in itself is a vector, so this is going to expand like this, that that we are differentiating vector F with respect to each element of x1. So the first entry is nothing but the partial derivative of each element of F with respect to x1 itself. So its ijth entry is nothing. So its ijth entry is nothing but del fi by del x. So it is nothing but the ith element, the partial derivative of the ith element of y with respect to the jth element of x. Okay, I mean, is it clear? So this is del f over del x prime, and so x prime means that we are stacking x's in the elements of x's in the row form and the elements of y in the column form.
Okay, ma'am. Thank you.
Okay, I mean, if there is any confusion, please let me know.
Ma'am, which book can we refer to know more about this Jacobian matrix and its stacking thing?
I think you can use Simon and Bloom. I am not sure whether it is there or not. But you can Google it. That's what I'm saying. I mean, can Google it also. I am not sure about Simon and Bloom whether it is there or not because I don't have any hard copy of Simon and Bloom, and neither the hard copy nor the soft copy. Uh, but see if it is there in green also or not. And if
Okay,
you
ma'am.
can't find any standard textbook, you can Google it and read about all these things. I mean, because these are the basic stuff where and you these are common stuff. So in every standard textbook, these things are going to be same. Maybe you find it in one textbook, but not in the other one. So if you are not able to pick any textbook, then you can Google it and read about all these things. The only important thing is about what is the concept and how to stack all these things. And even if you don't want to refer to any standard textbook, if you understood this stuff, that's more than enough. Your voice is not audible.
Hello.
Ah, yes.
In last class, you said that you used to take 2 weeks of preparatory classes. So have you covered all those topics in these 2 classes?
Yes, I have covered all these topics, but what I did the last year, I have started it with the matrices also. Like I have started with the scratch in the sense that I have started what is a matrix and what is a symmetric matrix, all those stuff which I have told you in the first class that you should know about all these things, because at the end these are the things which are important for you. These are the things that what I have taught you in these last 2 classes.
Okay.
And since I was running short of time, so I thought it's better that you read about matrices yourself, because what happens is that what was my experience was that few people are aware about matrices, only one or two are not aware about the matrices. So effectively in the first 2 classes, in the first 2 classes, whatever I was covering last year was like a waste for the other people. So that is why I told you that you please read about the matrices, properties, and the determinants and all these things on your own. And if still there is some confusion about all these things, you guys can come to me and ask me. Since I was running short of time, so I have thought to cover the more important stuff rather than covering the most basic stuff.
Thank you.
You can stop recording, right? And then you guys can ask questions.